Hello, in this demo we'll talk about why you should choose Portworx to run Kubeflow on your Amazon EKS clusters. For this demo we have a simple 7-node EKS cluster. 3 of those nodes are storage nodes which contribute storage, block and file storage for Kubeflow, and then the remaining 4 nodes are part of a node group that have GPUs in it. For this demo we'll deploy a few storage classes. The first one is called standard-sc. This storage class will serve read-write once traffic, and it will store 3 replicas for any data that's written through it and perform local and cloud-based snapshots. We'll have a schedule policy called weekly and interval, which takes a snapshot at every 15 minutes and then a weekly snapshot on Friday at 10 p.m. And then we can specify a retain policy for the snapshots. So we only store 5 snapshots at any time. And then we have a shared SC storage class, which will provide read-write many storage for Kubeflow and has a replica factor of 2. And it will basically allow, for this demo purposes, connection from any IP address. So let's go ahead and apply these YAML configurations. So we apply our schedule policy. We can verify that the schedule policy got created by using kubectl get schedule policy, and we can look at details by using the kubectl describe schedule policy and the name of the schedule policy, which is weekly and interval. Here you can see that interval minutes is 15 and then a weekly interval of Friday 10 p.m. We'll apply the 2 storage classes as well, standard and shared, and those are created on top of our Portworx storage cluster. We'll also make a couple of changes for our default storage class, so changing that from the AWS GP2 storage class to our Portworx standard SC storage class, and verify that the change was applied. At this point, we are ready to go ahead and install Kubeflow version 1.3. To do that, we'll use customize. We have already cloned a Git repo which has all the binaries needed or all the YAML files needed for Kubeflow deployment. And we use this one simple command. So customize deploys all the different components that you will need for Kubeflow, from service accounts, cluster role bindings, any deployment spots, service objects. All of that is automated and deployed on your EKS cluster for you. And all the persistent volumes are provisioned from your default storage class, which in our case is the standard SC storage class from Portworx. So any data that's written to that store, any persistent volumes configured by that storage class will have 3 replicas distributed across different nodes in the cluster. So we can do a kubectl get pods to verify that, okay, everything was deployed, everything is up and running correctly. And next, what we'll do is we'll port forward, because the Istio ingress gateway uses a cluster IP. We'll use port forward for this demo, so we can access the user interface for Kubeflow. We log in using the default credentials, which in this case are user@example.com and the default password. Once we have access to the UI, we know that our deployment was successful. So now let's go ahead and create a couple of persistent volumes that we'll use for our data preparation, training, and inference phases. So we have a datasets persistent volume and a models persistent volume. Both of these are read-write many persistent volumes. So our pods and stateful sets that are created for all these different stages in our machine learning pipeline can read and write data to a single source. So let's go ahead and create a notebook for our data preparation state. So we'll use a custom image and point it to the image and pick out the latest version of that image from Docker Hub. And then you can also specify additional parameters like the amount of CPU and memory resources you want to assign to these pods. If you want GPUs, but again, this is just data preparation, so we don't need GPUs for this. We'll create a workspace volume, a brand new volume, but then for data volumes, we'll use the datasets persistent volume that we just created in the last step. While the prepare stateful stat or notebook is being deployed, we'll go ahead and create additional notebooks for training and inference. So for training, we'll select the correct image, and in this case, we'll select a GPU instance. So one NVIDIA GPU is what we'll need. And then from data volumes, we'll connect the data sets persistent volume, because that's where our data will be. And then we'll also attach a models volume, which is where our trained models will be stored. So when we deploy the inference stateful set or inference notebook, it can read our or access our trained models from the model's persistent volumes and run inference. So we don't need any GPUs for this one. As a data volume, we'll just map the model's persistent volume to the inference notebook as well. Our prepare notebook is ready, so we'll just navigate to it and we'll create a new folder called raw and then upload our training data set to that folder. So let's just rename that folder and then we'll upload our zip file which has images of cats and dogs. We are running a simple machine learning app which basically trains itself on a bunch of images of cats and dogs and then runs inference for us where we provide it a random image and it will tell us whether it's a cat or a dog. So we are uploading the training dataset onto our datasets persistent volume. So this is something that will be stored on the Portworx storage layer. And once we have the training data uploaded, we'll go ahead and upload the data preparation file as well. So let's just select that and upload it to our data preparation notebook. You can access this Jupyter notebook and basically run all the cells. So this imports all the different modules that it needs. It unzips the zip file that we uploaded in the previous screen and goes through all the different steps that are required for data preparation. And this is where data scientists and machine learning developers who are building their own models can customize this Jupyter notebook, but still get a resilient infrastructure underneath. So even if their pod fails, their Kubernetes node fails, the data is persisted across these different different iterations. Now that we have the data preparation step done, we'll go ahead and perform training on that data. So we'll upload the training file, access it, and basically run all the cells. So again, this is something that the machine learning engineer or the data scientist will have and use Jupyter notebooks for. This basically is running on an EC2 instance, which has a GPU instance associated with it. And it basically runs 20 iterations, which means that it will keep running till it hits an accuracy percentage of 90%. We'll fast forward it as this takes an hour, or depending on the type of instance you have underneath. If it's CPU, it might take a day, but if you have multiple GPUs, it can get done quicker than an hour as well. Once the data training is done, or machine learning training phase is done, it basically saves the models on the model's persistent volume. So we can go back and access the folder structure and look at the models folder. We see a couple of .pb files, which are our trained models for this machine learning example. Now, the next step, once we have done the data preparation and done the training, the next step is running inference to make sure that the models that we have trained do produce accurate results. This is just a quick sanity check. So we'll upload the inference file and then run it. So what this does is it basically pulls a random image of a cat and a dog from the internet and runs it against our trained models, and we'll see whether we get the correct answer. So it chose a random cat image and a random dog image, and our model reported the correct differentiation or distinction. So I think we are good to go. At this point, we are ready for a couple of scenarios. We can transfer these trained models to different Kubernetes clusters, which may not have GPUs, which might be running at the edge locations, and just run inference there. But if you want to iterate on this model and you want to make sure that you have different snapshots at different time intervals, you can use the Portworx storage layer and Cloudsnaps functionality to store local and cloud snaps. Okay, let's look at the different snapshots that have been created for your persistent volumes. You can also use additional commands like stork_ctl get volume snapshots in the same namespace called Kubeflow user example.com to get more details around what's the persistent volume attached with it, are the snapshots ready, when was the snapshot taken, and you can basically use these local or cloud snapshots to restore your persistent volume to different points in time. Next, let's go into more details and see how Portworx helps with node level fault tolerance as well. So we configured our storage classes so they have for the read write ones, they store 3 replicas, and for read write many, which is our file based, they store 2 replicas of our persistent volume or our data on our Portworx storage cluster. So we basically identify, okay, our training notebook, which maps to a stateful set, which maps to a pod, is running on a specific node. We'll identify the node that it's running on. We'll describe and make sure that, okay, it's running on a node which has a GPU instance attached to it. So we can scroll up and see that, okay, it has one NVIDIA GPU, which is what the data scientist wanted to use from the user interface. And then next we'll log into the Portworx pod and look at how the replicas are distributed and how much utilization there is for that persistent volume. What are the different pods in that namespace that are consuming data or using that persistent volume to store data. So once we enter the Portworx pod, we can use a pixie-cuttle status command, a pixie-cuttle volume list command to find out more details. So the persistent volume ID is what you can use to identify as the name of the persistent volume. So let's go ahead and look at the actual persistent volume name for our model's persistent volume. So looks like we haven't run a kubectl get pvc command. So we'll basically exit out of the Portworx pod and run that command again to get the ID. So let's do a kubectl get pvc in the Kubeflow user example namespace. And here you can see that the model's persistent volume ends with a 9AE. So if we do a volume list again and grep for that specific volume ID, we'll get the actual ID for that volume at the Portworx layer. So now we can use a volume inspect command and provide that ID and get more details about that persistent volume. So here you can see that our inference and our training pods are actually using data. We have 2 copies that are stored on 53.50 and 17.235 nodes. We can look at additional statistics around the read latency, write latency, number of reads and number of writes. We can see that our HA is set to 2 and IO priority is set to high. So things are looking good. Things that, again, we didn't have to do any additional configuration. These were things that were specified as part of our storage class configuration, which the DevOps administrator can do. And those are automatically applied for any volumes that are created. Now let's look at the second use case where we use PX backup as the data protection tool for your Kubeflow instance running on an EKS cluster. For that, we'll add our EKS cluster to our PX backup instance using a simple command. So we provide the kubeconfig file, we say that it's an EKS cluster and select our AWS cloud account. It gets added and PX backup will basically inventory all the different namespaces and identify all the different objects that are running inside that namespace. So we can create a simple backup job. All you need to do is give the backup job a name, select a location, which is an S3 bucket. You can either do an ad hoc or on-demand backup job, or you can create a schedule for the backup job as well. At this point, PX backup talks to your EKS cluster and takes an application consistent backup job for your Kubeflow instance. So it not only protects your data and the models that you have trained, but it protects or backs up all the different Kubernetes objects, all the different application configuration that you have done as part of your Kubeflow instance. You can use the PX backup interface to protect a Kubeflow instance, but also restore it to the same cluster. Or if you want to move it to a different cluster, maybe running in a different cloud environment or an edge location, you can restore it to a new location as well. So PX backup can also act as the tool that can help you move your trained models to different clusters. You can use PX backups UI to monitor your backup jobs. You can use the backup timeline to go as back as 24 hours or 30 days at max. Once the backup job is successful, you can do show details and look at all the different persistent volumes and Kubernetes objects that have been protected. At this point, let's just simulate a failure and delete all the notebook instances and all the persistent volumes that were created for our Kubeflow instance. So we'll delete all the data preparation, training, and inference notebooks. We'll delete all the volumes that are associated with it. And once they are deleted, we'll go ahead and perform a restore operation for our Kubeflow instance on the same cluster. So at this point, you can hit restore, give the restore a name, and then select the destination cluster. We are restoring it to the same cluster, so we'll select the same cluster, and then we'll select all the different objects. So optionally, you can select different resources. So if I just want to restore persistent volumes, you can do that too. Once the restore is successful, you will see that your persistent volumes are bound again. Your pods in the Kubeflow user example.com namespace are up and running. They go through the same deployment process. So it takes a few minutes for everything to be back up and running and your restore to be successful. But once it is, let's just verify that everything still looks good. So we'll connect to our inference notebook and run through the same workflow where we pull a random image of a cat and a dog and then run it against our trained models just to verify that our whatever model that we had created is still valid and it still runs as expected. So the image of the cat comes out as a cat, and then the same image of a dog does come out as a dog as well. So we are all set. Next, let's talk about how we can take the model that we have trained on a GPU enabled cluster and move it to a completely different cluster. In this example, we are using just another EKS cluster, but again, you can move it to any other Kubernetes clusters that attach to your PX backup instance. We'll give the restore a name, select the second cluster, and then we'll perform a full restore as well. So we'll replace all resources and basically restore everything that was part of that backup job. You can monitor your restore operation from the UI or from the CLI. So you can have a watch command for kubectl get pods, and you can look at the different pods being spun up for your Kubeflow or for your Jupyter notebooks. Once all the pods are up and running and the restore operation has succeeded, you can go back to your Kubeflow instance. So let's log into this new instance that was created in the second cluster. So we log in again as user@example.com and the same default password. And here you can see that, okay, my inference notebook is up and running, preparation and training are still going through some final steps, and all our persistent volumes are back. We'll run a quick inference task again. Same thing, a random image of a cat and a dog, and run it against our trained models to verify that the model is still correct, and I can use this model that somebody else has trained for me in the cloud. This is how Portworx can help users who are working with Kubeflow and Kubernetes. Until next time, thanks for watching.